proportional derivative controller design. And this is sort of you're getting to see just like the very beginnings of controller design techniques, but you have enough tools to do quite a bit now. We have the ability to adjust the gain to build a proportional controller and change what the transient response, for instance, is going to look like for a system. And we also can add in an integrator or a lag compensator for steady state error improvement. And then one limitation that we've had thus far, though, is that we've been restricted to the original root locus for the most part, right? So we can vary the gain, we can move the closed loop poles around on that root locus, but we were sort of stuck there. So if you wanted to be anywhere besides where the root locus happened to be for that system, you didn't have any way to get there. And so this lecture will give you one way to move the root locus around appropriately so that you get a specific closed loop pole location that you desire, even if it's not on the root locus. Okay, so among many possible methods to address this moving of the root locus around, we pursue the following. A derivative compensator with zero location ZC chosen such that the root locus intersects the closed loop pole location that we desire with form 611. So we've got a single zero located at ZC, and we've got a gain associated with the compensator as well. So that's our goal, is to use this to move that root locus around. Now we just know to figure out how to move it around, how to choose especially ZC so that we have an intersection with the closed loop pole location we desire. So this compensator is called derivative because its primary effect on the overall controller's operation on the error E is a new factor of S, yielding a scaling of the term S E of S, which is, of course, in the time domain, the time derivative. That's why it's called a derivative compensator. Okay? So it's the effect of the zero is to pull the locus toward it. And I want to sort of step back for just a moment and say, no, we'll just go forward with this. I think this is good. So consider the simple plant of figure 6.8. So this is a root locus plot for a plant with a pole at -3 and a pole at -1. Okay? So we could sketch this, and it's got two zeros at infinity, and we do all that. Oh, you guys, it's super light, isn't it? This is an axis you can't really see.
You can see it on the sheet, though.
Yeah, make sure it's printed out. Yep.
Something I forgot to bring up today.
Yeah.
Does that graph have asymptotes?
It does.
Because that asymptote question on the quiz last week just made no sense to me.
Okay.
I thought it had 2 asymptotes and then it had 0.
Okay.
I didn't understand.
Let's ask on Slack, and I'll review it and make a ruling. Maybe people will get free points.
Okay.
Yeah. This has 2 asymptotes because it has the same number of asymptotes as it has zeros at infinity.
Right.
So, yeah, maybe the quiz question was wrong.
Yeah.
Quite possibly wrong. It wouldn't be the first time. So this is our root locus in blue. And say we desire to have a closed loop pole that made it so that the speed was faster. So say we want to speed up the closed loop response, but cannot because no matter how much gain we use, the settling time is fixed by the vertical asymptotes. So as you increase the gain, the closed loop poles start at these open loop poles and they move in, and then they split off and they go straight up and down. But remember that the settling time is governed by the real part of the closed loop poles. And as you increase this gain more and more, the real part of this closed loop pole stays at -2. Doesn't change, doesn't get any faster, right? The settling time is going to stay the same. So by increasing the gain, we can't get a speed up. So we want to speed up. We want these closed loop poles to be over here, for instance. But the root locus doesn't go through that point. So with our old techniques, we don't know how to do that. So that's why we're introducing a new one. If we use a compensator 0, ZC, we can pull the locus leftward, as shown in figure 6.9. So if I start ZC at -10, notice that the locus, instead of going straight up and down like it did before, it got pulled leftward, right? So now we could intersect a pole that was like here, for instance. We could intersect the point that was there. Our closed loop poles could be there and there, or here and here. So you can vary ZC and notice that you're going to move where the locus goes through. So, and in fact, this covers, I mean, we just showed, a couple snapshots here, but this covers the entire plane left of -2. We could go through any point we desire in the plane by moving ZC around. And there's a little animation that I made. I spent way too much time making, so we're going to watch it. So this is the same plot, but instead of 6 snapshots, we're going to watch it continuously vary. So I'll pause it there. Notice as we're moving this compensator 0 rightward, this circle is closing down, collapsing, and if we continue, we get to there. So, it doesn't continuously update. That sucks. But that's the general idea. So if we knew a certain location that we want our closed loop poles to be, we could choose our ZC such that the root locus goes through that point. Now we just got to figure out the maths that make that happen, right? How do we choose our ZC to make it go through a certain point? And another point that's kind of interesting about this is that if you consider negative gains, which we could consider negative gains, we typically don't when we draw root locus, but occasionally it's useful too. We could actually cover every point in the right half plane as well. We could cover everything to the right of -2 as well. So you can make your root locus intersect any point in the entire complex plane. It comes at a cost, though. I mean, there are some times when you would have to have really, really massive control effort to make that happen. But that's the idea, though, is that you could do it in theory. But you can't place. So you can place a single pole anywhere you want and make the root locus intersect it. But you only have the ability to do that for one pole location. You can't arbitrarily set all of your pole locations. So there's another controller design technique, pole placement controller design technique, that lets you place all the poles wherever you want. That requires more adjustable parameters than we have. We only are adjusting one ZC, so we only get to choose one point to intersect. But usually that's enough for a lot of systems. So it's pretty good. Look at that, 6 views. It looks like I've watched it 6 times. Yeah, nice. Cool. So this is the idea. A way to approach designing a controller for plant G with a derivative compensator C is to consider the compensator 0's effect on the phase criterion, which must always be satisfied at points on the root locus, right? That was how we first derived our rules for sketching the root locus, was from the phase and the magnitude criterion, right? So here is the phase criterion, just for any point on the root locus. So this is the plant and this is the compensator. So we have to have the plant and the compensator angle has to be equal to pi in order for us to have locus at that point, right? That's the criterion, that's the condition we have. So if this is satisfied for a given value of s, it's on the locus. So that's going to be useful because we want to have a very specific point be on the locus in our the locus we're gonna come up with based on choosing this compensator a certain way. So 6.12 is where we start. In order for a desired point s equals psi to be on the root locus, then we need the angle of g of psi, c of psi, to be equal to pi. Now I'm dropping the plus 2 pi, plus 4 pi, etc. because it just, I think, is a little simpler to look at. But you can go around and it's equivalent to be at pi and 3 pi and 5 pi, etc. You guys are all familiar with that modulo operation, right? So this angle, remember when you have two angles, we have an angle of two systems that are transfer functions that are multiplied together, then you can take the sum of each angle separately, right? Angle c of psi equals pi. So we can then rearrange this, such that we have the solution for the angle of c of psi, which is equal to pi minus the angle of g of psi. So we just subtracted the angle of g of psi over. And if we plug in our form of our compensator, so the form of our compensator is a gain times a 0 at zc, right? The gain doesn't affect the angle at all, right? It's the magnitude of the vector, but that doesn't affect its angle. So what we have is the angle of psi minus zc equals pi minus the angle of g of psi. So let's think about this from a sort of geometric point of view for a second. If we've got our, I'll just use this graph actually. Say this was the point that we're trying to get to. This is our psi, let's say. And I'll clean this up just to make it a little less confusing looking. So there's our psi we want to be at. We have this, we know that if we evaluate g of psi, it's not going, the angle of g of psi, it's not going to be equal to pi because it doesn't go through the root locus. We're trying to place our 0 in a location such that it contributes an angle, so I'll draw it right here. It contributes an angle like this. So this is our ZC, this is our psi. We're looking for the angle of psi minus ZC. Thinking in terms of vectors, the angle of psi minus ZC is the angle of the arrow that is drawn, or the vector that's drawn from ZC to psi, right? So it's this angle. And we call this angle, so this is the angle of psi minus ZC. We just call that theta C, the compensator angle, okay? So we need this theta C to be such that the magnitude, or the phase criterion is met at that point, right? So that's our goal here. So theta c is the compensator angle that we need. So now we need to know, so we don't get to choose the compensator angle directly typically. What we're trying to choose is where ZC goes, right? So we got to back out where ZC should be to make this angle theta c. And I did the trigonometry for you. It's the real part of psi minus the absolute value of the imaginary part of psi divided by tangent theta c. So if you want your angle to be theta c, in order for our root locus to match the angle criterion at that point, then you would choose 614 to be your ZC. This result can be used in the design procedure that follows. It can be understood geometrically as the position of ZC such that the angle of the vector with tail at ZC and head at psi is theta c. Okay, so that's sort of like the derivation. We'll talk through the design procedure, and we'll just use the results of this derivation for our design procedure. And then we'll do an example. I didn't have a chance to write the example because it was 3 a.m. and I wasn't functioning well enough to continue writing up notes. So I shut her down. We're going to do the example live. It'll be fine. Okay, so good. The following procedure provides a starting point for proportional derivative controller design. Let's assume the transient response specification is such that we desire a closed loop pole to be at location s equals psi. So actually figuring out where you want your closed loop pole location to be. I mean, you have as many closed loop poles as you have order of your system, right? So in the case example up here, we have 2 closed loop poles. You only get to choose where one of them is. The other one is wherever it happens to be. So they're not always going to be the dominant ones, but sometimes they'll be the dominant closed loop poles, and some of our second order assumptions and all that will hold true. So let's give it a shot. Let's go through the design procedure first, and then we'll explain. So we want the closed loop pole to be at psi. First step is to design a proportional controller to meet the transient response requirements by choosing the gain K1 for the dominant closed loop poles to be as close as possible to psi. So we want to put our closed loop pole location at psi. Let's try proportional gain to see if we can just do that with a gain. We might get lucky and it'll just happen to go through the point we want. The root locus will. It's probably not going to happen though, right? Probably we're going to want to do better than whatever the system happens to do with a proportional gain. So we design a proportional controller. We see how it does. If it doesn't go through psi, we have to continue with cascade derivative compensation. So that's step 2. We include this compensator. We'll initially set this compensator gain to 1. We'll just say, okay, for now, we'll just set it to 1. We're going to focus on placing that 0. That's what our focus is going to be. So placing that 0 is kind of like the first challenge in this problem. Yeah, doing the root locus and figuring out what gain you need for the root locus is step 1. We're getting pretty comfortable with that, hopefully, at this point. And now we're ready for the next challenge, which is relocating where ZC should be to match our transient response characteristics. So maybe it's a settling time or a percent overshoot response requirement. It'll give us some guidance on where to choose psi. And once we know what psi is, we can determine what ZC is by using these 2 key formulas. So I've repeated the 2 key formulas. Essentially, these are the 2 formulas you need to compute what your ZC location should be. Now, these aren't always trivial to compute. And so if you're thinking about like final exam, how am I going to do this? Well, probably, it's going to be either relatively easy to compute using the equations, or you can use a geometric approach where you look at this sort of angle criterion and making sure that it matches. So you might have options. I mean, there is like a whole lot of different ways I could go with asking you this. If you understand how it works, then you should be fine. Brute force computing is good when you have a computer. It's sketchy when you don't have a computer because sometimes computing the angle of this is a bit of a pain. So you have G, which is a transfer function. So you have a bunch of places where S shows up in the transfer function, right? And you got to plug in psi whatever that point is. So like you could have like S plus 2 divided by S cubed plus 4S squared plus 3S plus 5. And if you want to evaluate that at psi, so like evaluate it at say like S equals psi equals maybe -2 plus J5. See, that's where you want your closed loop pole to be. You got to plug that in for S everywhere here. And then you have to simplify this down so that you have a real part and an imaginary part. And then you got to take the arctangent to find the angle. Okay? And then you got to take pi and subtract that angle. It's a pretty involved computation. So I'm going to try to make it so that you don't get caught up in all of the weeds of computation, but also be prepared to do some computation too. So anyways, that's like, I have to come up with a way to make that happen. But in MATLAB, you can this is just like a one-liner, right? Just bam, plug that in and you're good. ZC, then once you know theta c, you're ready to plug that in and take the real part and imaginary part of psi, which is relatively way easy. Take the tangent of theta c, which is also relatively way easy. And then you have your ZC. So that is the procedure for finding where your ZC should be to make your root locus go through psi. It's not terrible, but by hand it's a bit of a bear.
Dr. Cody?
Yeah.
For this particular topic that we're talking about, would this be, I guess, the last bit of chapter 9 then? I'm making sure that
yeah, so in the Nice textbook, this would be, I don't know if it's the last bit. It's definitely in chapter 9, somewhere in the meat of chapter 9. Yeah.
I just want to make sure that I'm not, so when I study it, I'm going to go back to I want to make sure I'm corresponding to my materials.
Yeah, and Nice has got some really nice examples too of PD controller design. So yeah, all of the controller design techniques that we've learned so far, there are good examples in the Nice textbook. So even if you haven't...
Chapter 9 focuses on the design part of it.
Yeah.
And then chapter 8 focuses more on the just solving it, I guess.
Right, doing the root locus, like constructing it and all that, yeah. So I think, yeah, if you understand chapter 9 and can do the chapter 9 homework, and that's part of why I'm like continuing to keep this quiz on the books, just to like, I really think it's like free points if you do the homework, and the real important thing is to do the homework so that you're ready for the exam. So I don't know. If you guys don't want to quiz this Friday, then like start a Slack poll or something, and I'm fine with that. It's really up to you. I figured that you guys would want the extra points, but if you don't want the extra points, you don't need them, so that's fine. Whatever. If you like your quiz grade and you're happy with it, you just stick with it. Okay, so so now that we've got ZC, we have our compensator in there, but our K2 is just 1, right? We haven't changed K2 at all. So we'll do a new root locus to tune K2 such that the closed loop pole is at psi. We should be, as long as we haven't rounded too much in our calculation, we should be able to get it right on psi. Right? That's the theory, is we should be able to. Of course, if we rounded anything along the way on our calculation or estimated it, we'll just be close, which is often okay because our performance criteria. Wow, apparently I told her, hate to set up the clothes in the pool. Is that we should be along me up at root, should be able to get it right. And she said, good morning. I have British Siri or Australian. I think it's British. There's also Australian. Which I was like, you're too chill sounding. You got to be a little bit more like on it. British is like, I want my personal assistant AI to be not too low key. You should be a little wound up, like me. Okay, so 4, construct the closed loop transfer function with the controller. So now we've got K1, K2, and ZC. So now we're ready. We can use this controller, and then we simulate to see if it meets specs, and then we tune. So that's the process. I'm going to try to go through an example with you guys in the next 20 minutes. See how this goes. Any questions before we begin? All right. So I took the liberty of defining, using ZPK, a pretty simple transfer function with 3 poles, no zeros, and I say design a PD controller for 15% overshoot and settling time of 0.2 seconds. So I give 2 transient response characteristics that I want, okay? Let's think about these 2. Percent overshoot is directly related to the damping ratio, right? And the damping ratio is directly related to the radial angle from the origin, right? So I'm going to go back and remind us from chapter 3 that, first of all, percent overshoot. This is in the transient response characteristics lectures. That the percent overshoot and zeta are directly related. You can solve for one given the other. So given 15% overshoot, we can solve for a specific zeta. And given a specific zeta, we know that we have this angle. Okay? So our cosine of zeta determines the angle here for our dominant second order poles. Assuming that we have a second order system, assuming that the second order approximation holds. Because this is not a second order system, it's a third order system. So assuming it holds, we want zeta to be at a very specific angle here. So we've determined that with 15% overshoot. There's a very specific angle. We haven't solved for that angle, but there is one. Okay. The other thing that we know is with the design spec is that we need 0.2 seconds of settling time. So you may or may not recall that settling time, we have this nice formula, 4 over zeta omega n, which is related to the geometry here as being the real part of those closed loop poles, the magnitude of the real part of these closed loop poles. So it's this. So if we have determined the real part and this angle, there's one location where they're both met, right? So we should be able to solve for that using trigonometry. It's a triangle. It's Alt-J's favorite shape. 3 points where 2 lines meet. Tessellate. Okay. I listened to that in the shower this morning. That's why I was thinking of that song. It's very rare that I have that close of a connection to an Alt-J song. Okay, so we first, let's determine, so we're essentially looking at a triangle, right? We need to do this trigonometry. And I'm just going to, and this is not related to the design procedure in general, but what we have is, for this example, we want to place our psi so our psi is there. We want to place that at some real part, right? So this value should be equal to, this is zeta omega n, which is the real part of psi. And we also have a prescribed angle which we could call like theta sub psi or something like that. That's related to our zeta, which is related to our percent overshoot. So we need to determine those and do some trigonometry to figure out what psi is. Okay? So that's our first goal. We got to figure out where our test point is, where the point we want to intersect with our root locus is. We can't really do anything until we figure that out, right? So we've got to figure that out first. So in MATLAB, let's do root locus, just a simple root locus of G. And we'll just see, oh crap, yeah. I just figured I have to restart MATLAB. Oh, okay. I was going to show you guys, in addition to the video, how to use CISO tool, but I want to show you guys too much in one day. I can't show you everything. Okay, so while that's booting up, we have our, let's figure out what the real part is, because that part's pretty easy, relatively easy, right? So we got to find out what the real part is based on our settling time. So the formula from equation 311 is 4 over zeta omega n, which is equal to 4 divided by the real part of psi, which implies that the real part, this is real, not just r, which implies that the real part of psi is equal to 4 divided by ts, which is equal to 4 divided by 0.2, which is what? 20, yeah. And actually, I should have put a negative sign here. It's the negative real part of psi. It's 20, therefore, actually I'll do plus here and minus, minus, minus. Okay, so this should be at, so psi's real part should be at negative 20. So psi is equal to negative 20 plus j, whatever its imaginary part is. Now we've got to find out what this imaginary part is of psi. And we've got to figure out what the angle is in order to do that, right? So we can go back to our formulas.
Sorry, the points, what is
The 0.2 is the settling time of 0.2 seconds.
Where did the 20 come from? I'm sorry.
It's 4 divided by 0.2.
okay.
Yeah. Yeah. So now we got to figure out what this imaginary part is. So we got to figure out what theta psi is, right? So let's use the formulas. Let's use the formula from here. So this is the zeta formula, and we'll be able to go from zeta to theta. Zeta to theta. We could start a frat. It would be fun. Okay. So we'll look at the root locus in a minute, but let's find psi. So we know that we have psi real is equal to 4 divided by ts. Our ts requirement was that would be at 0.2. And negative. And that was the one we just did, right, by hand. But now we need to know, it wasn't just ts that we were given, it was also overshoot, be 15%, right? So now we need to solve for zeta, I'll just call it, yeah, I'll call it zeta. It's equal to negative log, how do you do natural log in MATLAB again? Is it ln?
No, it's just log.
It's just log?
Yeah.
Oh yeah, log 10 is log base 10, that's right, okay. Negative log of overshoot divided by 100 divided by square root of pi squared plus log overshoot divided by 100 squared. So there's our zeta. Our zeta is 0.52, okay, which sounds about right. That passes the BS test. So let's back out. So we know that the angle is equal. Our theta psi is equal to the arc cosine. Is it arc cosine? Or a cosine? Arc cosine?
I think it's a cos.
It's
A cos of zeta. And let's compute that. Yeah, so that makes that makes sense. If we did theta psi times 180 over pi, we get about 60 degrees, which sounds reasonable. That sounds about what that angle should be. So there's our angle. And now comes some trigonometry. How do we determine, if we know what theta is and we know what the real part, this side of the triangle, how do we figure out what that part of the triangle is? Yeah, so tangent of theta psi is equal to the imaginary part of psi divided by the real part of psi. And therefore, the imaginary part, well, and actually, we don't even, so the imaginary part of psi, which is what we're solving for here, is equal to the real part of psi times tangent of theta psi. So we can say that psi imaginary is equal to psi real times tangent of theta psi. And did I do something wrong there? Oh, I need the positive of real, right? Because the real is negative, but this is just, we're using it the distance and not the direction. So we need to do absolute value of psi. Okay, so 33. So negative 20 and 33. So that means that our psi, we can even define it if we want to. Psi equals psi real plus, and then in MATLAB it's I, right? Capital I? No. Just little I, or J. Yeah, I haven't used either yet. It's nice. I always overwrite those with indices, unfortunately. J times psi imaginary. So there's our psi. Whew! We found it. Now this stuff makes great fodder for exam questions, right? Some good old-fashioned trigonometry, geometry, not too bad. So yeah, but without using MATLAB. So I mean, these are all things you could type into your calculator, though, right?
I would hope so.
Yeah. Well, I mean, yeah. Okay. So now that we've found psi, let's look again at our root locus. We didn't really ever get a chance to look at it because the screen was all wonky. Okay, root locus. We want to be at, our test point is negative 20 and 30. It's like way up here. Not even close whoa. It's like, it's not even close to our root locus is way down here. There's no way to even get close. So I'm not even gonna bother trying to get close with a gain here. You could try to get close with our proportional controller, but there's not even any point because we're like not even in the ballpark, right? You could get percent overshoot right because it's the angle, but there's no way we could get settling time. We'd be off by a mile. So let's just focus for now on doing a derivative compensation, derivative compensator. So our compensator, let's call, we only have one gain because I'm not doing a proportional gain, K1, so we'll just have K. So we'll do K equals 1, and then we'll say that our compensator is equal to K times, or I guess we could use ZPK of, we're going to put our ZC in here, which we need to compute, and our gain of K. So we got to compute our ZC. We're ready for that point, right? So we got to compute ZC. We've got our two formulas here. We got to compute theta C and then ZC first. So, are you guys ready? Okay. So the first thing to do is to compute G of psi. So MATLAB has a nice function for that. So we don't have to do all this by hand plugging in stuff. But it's called eval fr. Okay. So what we can do is first we'll find theta C.
Eval FR. Just write down the exam.
Yes. I mean, and like I frankly could ask. I'm going to ask you guys things about MATLAB in it because we've done so much MATLAB, but just not anything we have to actually program. I won't have you guys write a function file by hand. I won't do that. Okay, so theta C is equal to pi minus this angle, right? So angle is an actual function in MATLAB, and we can do eval fr of the system, which is our G, right? And then the frequency, and this also corresponds to any complex function. So you can actually evaluate, they're thinking frequency response by FR, but you can also have it evaluate a complex number. So we want to have it evaluate psi for us. Okay? So let's just, I'll comment this out. Let's just see what that gives us. So that's our theta C. Theta C times 180 over pi, 156 degrees. So that thing has got to be way out there. It's got to be almost pi, right? I mean, not quite, but it's getting in that ballpark. So this is pretty intense angle here. But in theory, it should still work, right? So there's our theta C. And our ZC is the real part of psi minus the absolute value of the imaginary part of psi, just using the formula, divided by tangent of theta C. So our ZC has to be at positive 56.67. So it has to be way over there, which is kind of an odd thing, but is actually the case. So let's do our compensator then. And I know it's like time, and also I'll try to just like, hopefully we don't screw something up here. Let's close the loop and simulate it. So let's do G closed loop equals feedback. We'll put in our compensator. Oh, we haven't chosen our gain yet, so we'll have to do a quick R locus. And if you have to go, I get it. It's no big deal. I think we took the wrong branch cut. Oh, I know why. Not of C. C times G, right? There we go. So see if we can find our point. Like that will at least be our goal here, right? If we want to be at negative, what was our psi? Negative 20, 33. Negative 20. Negative 20, 34. So yeah, I mean this is, we got it. We just have to, yeah. So we choose our gain to be, so let's call it 632. That's close. We could get a little bit more precise, but we could say that our gain is 632. So let's do our closed loop as being 632 times C times G unity feedback, and then let's do step of G closed loop. Whoa, did something wrong there. And now I lost my. Oh, I know why. This is why you don't do these examples without trying them first. I was a little too aggressive with my choice there. Because what happens, like, yes, we can make the root locus go through this point. This is where we wanted, right? But what happened to our stability? This pole is going to end up in the right half plane at that gain. So if I look at 632 for our gain over here, we've got a right half plane pole, so it's unstable. So we did succeed at making our root locus go through the point we desired, but we ended up with an unstable system, which is a bummer, right? Total bummer. But that is what can happen when you can't specify all three poles. You can't do real pole placement. You only place one at a time. You only got to choose one. You couldn't choose all three. So ideally, I would have been a little less aggressive with my choice of transient response requirements, and we wouldn't have gone unstable. But I made it up right before class, so that was why. I will try to do an example that works out for you guys, just so that you guys don't have. It was a good learning experience, though. I hope. Okay, I'll see you guys later. Study.